Okay, this is going to be a very extensive set of videos, and you're going to have several days to complete all the other numbers on the monster bonding assignment. In this video, I'm going to talk about what electron domains are. I'm going to talk about what the electron geometry is, which is what this column is right here. This is electron geometry. I'm not going to write it out, okay? This is what's called the molecular geometry. This is just the bond angle around some atom. This is saying whether a molecule is nonpolar or polar, and we got to really get into that. There's a separate video on hybridization. And this column really is important right here because it's really two columns. This is talking about the domains, the electron domains, and some of them are bonds, and some of them are lone pairs. Now, I'm not going to try to do this in 3D. There are lots of videos in 3D that you can watch. I'm going to try to explain how to use this chart to enable you to fill out the monster bonding thing, okay? And I will try to be as descriptive as possible in terms of visualizing three-dimensional shapes while looking at two-dimensional models. All right, let's start with things that have, let's start by explaining what a domain is first, or electron domain. So here's what a domain is. It's a region with electrons. Now, a domain could be a single bond. It could be a double bond. It could be a triple bond, or it could be a pair of electrons. And what happens is, when you look around an atom, there's going to be a certain number of domains around that atom. So let's just look at a couple of examples here, okay? And if you want to pause and try to guess, I'm going to put them underneath all these models, and I'm going to explain a few of them. So I'm going to start here. Underneath the beryllium, there's these two bonds right here, which means there are two domains around the beryllium. Around carbon dioxide, there's one domain. That double bond is a single domain, and then there's another domain, right? Around this carbon, there's one domain here and one domain over here. That's two domains again. So all those examples, and the top three examples of molecular substances, all have two domains around them. BCl3 has 1, 2, 3 domains. How many does this one have? Well, it's got a double bond here, a single bond here, and a pair of electrons here. Now, this is an example of a molecule that has 3 domains, but 2 of them are bonds and 1 of them is a lone pair. And we're going to have to look at that when we're trying to determine what the three-dimensional shapes of these molecules are. Okay, let's go back and let's start from the beginning here. Okay, I'm going to do a little bit of erasing to the best of my ability. And I'm going to first do this page here, which is on things with 2 domains or 3 domains. And then we're going to go back and do other videos on 4, 5, and 6 domains. Okay, you have this chart in OneNote that you can use. Okay, so let's start off with these first 3 molecules, all right? Let's talk about it. Now, each of these first 3 molecules, molecule BEF2, carbon dioxide, and hydrocyanic acid, all 3 of those molecules basically have a central atom around which is 2 domains. And there's no pairs of electrons here, so we don't have that filled in. This is not there. All right, so if you only have 2 domains, you can think of them as like basically a bond. These are sigma bonds, right? Or this is sigma and pi bonds. Well, those regions with electrons are trying to get away from each other. So you have like one dot here, and there's a region here with electrons. It doesn't want, the other region with electrons does not want to be there right next to it. So it moves to be as far away in three-dimensional space as it possibly could go. Well, where would that be? 180 degrees away. Any other place it would go would be an angle smaller than 180 degrees. So if you have 3 atoms, okay, or you have 10 atoms, but you're talking about one atom, and that one atom is surrounded by, has 2 domains around it, okay, those 2 domains are going to move away from each other and be at an angle of approximately 180 degrees. They wiggle, but that's the approximate angle. Now, that gets us to there. And that gives us a molecule that's linear, right? So linear means a straight line. So if this is the atom here and this is the other atom here, since the domains, right, this is domain 1 and this is domain 2, but this is the atom, the atoms end up being in a straight line. It's linear. Okay, now it says here the molecules are nonpolar. This is not always true. But let's explain what it means to be a polar bond versus a polar molecule. Let's get that out of the way now. Now, if you took Regents chemistry, your teacher probably talked to you about the SNAP method and stuff like that. That will sometimes work here. It would be better to just memorize this chart, okay, honestly, or to visualize things in your brain, which is the best really way of doing this and understanding it. Also, it will allow you to explain why a molecule might be polar versus nonpolar. All right, if there's 2 different nonmetals, the bond is always polar. And bond polarity means the electrons are being shared unequally. And if you remember, it has to do with electronegativity. So fluorine is more electronegative than beryllium. Matter of fact, just to make sure we're clear, fluorine is the most electronegative element, oxygen is the next most electronegative element, and nitrogen is the third most electronegative element, right? And that's going to affect the bond polarities because those atoms are going to be pulling electrons towards them, which means even if they're sharing electrons, the sigma bond or the pi bonds, they get deformed. And so instead of the electrons being evenly distributed inside that molecular orbital, they tend to be shifted over towards the more electronegative atom. So what will happen here is you get what's called you'll get an individual bond polarity, right? And watch how this works. This fluorine is pulling it this way, and there's another fluorine that's pulling electrons. That's just a smudge there, pulling things exactly this way. Now you notice the little pluses at the end. Now, this molecule is what they call the symmetrical molecule. I don't know if that's as acceptable on the AP exam to say that it's symmetrical. What you really want to say is that the individual bond polarities cancel each other out. And at this point, you've taken physics. You can think of them as vectors, right? If you had one vector going this way and an exact equal force, another vector going this way, right? And, they were both pulling on some object X, the object wouldn't move. That's going to give you a molecule that's nonpolar. So whenever the individual vectors cancel each other out perfectly, you get a nonpolar molecule. Now the good thing is, in any linear molecule where the two outside atoms are exactly the same, they will cancel each other out. So carbon dioxide has, even though it's a double bond, it has one domain. The oxygen's pulling that way. This oxygen's pulling that way. They cancel each other out. It's a nonpolar molecule. However, be very aware, it's different for number 3. And that's why this is like sometimes. Sometimes being there's a central atom and there's two other atoms, and the two other atoms are pulling exactly equally, right? So in this particular case, watch. The nitrogen is more electronegative than the carbon, and the carbon is more electronegative than the hydrogen. Now think to yourself, do those two bond polarities cancel each other out? If those are vectors, right, they don't add up to 0. That's not what the net force would be, right? And so for this molecule, this would be a polar molecule with polar bonds. Now, all these molecules have polar bonds, right? That they all have individual polar bonds. That's what those arrows represent. But in this case, the polar bonds don't cancel each other out. And the arrow points toward the side of the molecule that's negative. And this is why they call this a bond polarity. They say it's got a dipole moment. So I'll write that word down. Dipole moment. And what that means is it's got one side that's permanently negative and one that's permanently positive. So in this particular case, this side is permanently negative, and that symbol means partial. Okay, it's not like a -1 or -2. It's a fraction of that. So that stands for partial negative, and this side is going to have a partial positive charge. And so this molecule has two poles, one side that's negative and one side that's positive. Now, in a really large molecule, you can have pieces that are negative and pieces that are positive all over the place. But in a small molecule, like 6, 7 atoms, 4 or 5 atoms, you're going to have one side that's negative and one side that's positive. All right, so let's talk about when you have 3 domains. All right, so I'm going to do a little erasing to make things a little neater here. I'm going to erase all this stuff and this stuff here. Just get this guy out of the way too. And let's talk about these 3 molecules down below. Now, both these molecules have 3 domains around them. The difference in this case, however, is that in one of the cases, one of the domains is a lone pair of electrons. Now, again, I'm not going to talk about what's happening around the atoms on the outside, just around the central atom for now. So what you can see is BCl3, right, has 3 domains. All right, and so they're going to try to get away from each other as far apart in 3-dimensional space as they possibly can. And that's where you get this thing called trigonal planar. Now, that's the domain geometry. Now, in this case, you'll notice if the number of domains and the number of bonding domains is the same, you'll notice that the name is the same. So things that have 0 lone pairs, the electron geometry matches the molecular geometry. However, and let's take a look at this. Think about this in 3-dimensional space. Now, this looks like a Mercedes symbol, right? Or a peace symbol. No, I think a Mercedes symbol. No, peace has an extra line in it. All right, so you've got one vector pulling this way. Chlorine is more electronegative than boron. Another one pulling this way. Another one pulling this way. And again, you kind of have to visualize this, okay? In 10th grade chem, some teachers, myself included, mentioned the SNAP method. Well, this doesn't look symmetric, but the Regents accepts it but the reality is what's really happening here is you can if three people were pulling with equal force at 120-degree angles on something, right? Then those three vectors would cancel each other out, and the object in the center wouldn't move. So when you have something like this is a nonpolar molecule. The angle is 128 degrees. Now the hybridization sp2, again, there's another video on that, so I'm not going to get into it. Okay? And so this is a nonpolar molecule. But be aware, if this had been like BF, like something like this, where the atoms were not the same, then the bond polarities would not be the same. The fluorine would be pulling harder, and so this side would end up being negative, this side would end up being positive. So, but if it's a trigonal planar molecule like this, okay, and the three atoms around the center are exactly the same, it is a nonpolar molecule. Now for SO2, we have a different situation. For SO2, there are three domains. You have this thing right here, this here, and the third domain is a lone pair of electrons. So you've got two bonding domains and one lone pair domain. And what ends up happening here is the lone pair, okay, acts as a domain. They try to get 120 degrees apart from each other, but what happens here is one of the O's is here and the other O is over here. I'm not going to finish putting all the dots on, right? Now, look at the difference now. Now, the shape of the molecule here is not trigonal planar. The electron domain, the electron geometry is trigonal planar, but the molecule itself is bent. And the angle is a little bit less than 120. The reason why is lone pairs tend to repel a little bit extra. So you get an angle that's a little less than 120 degrees. So this angle here is about 120 degrees. And And now, notice, it says this molecule is going to be polar because look at it. The S is pulling this way. The O is pulling that way. The O is pulling this way. The electrons aren't pulling the other direction. They're not a bond. They don't have a bond polarity, right? So you get these two polar bonds. In this case, the vectors don't cancel each other out, right? And if you can imagine, if you were pulling this way and I was pulling that way, and we were pulling at 120-degree angles on some object, it'd be like a slingshot, right? And so this side ends up being partially negative, and this side ends up being partially positive. So things that are bent tend to be polar, all right? So now I'm going to do things with four domains, all right?